Hi, this is Dr. G. Bailey. In this video, we're going to do data measuring. We're going to do two types, chi-square and quadrisampling, which are found on topic 4. These usually fall in the IB exams, so it's very important that you know how to use them and why you're using them. So we're going to do two things. We're going to test the association between two species by using the chi-square test as well as the quadrisampling. And we're also going to look at it and interpret all the statistical significance of it. So first, let's start with the random sampling and understand how it works. Now, this technique is just to determine the frequency as well as the distribution of species. So for example, you can see this picture, you have this large land here of grass, and somehow we want to find out how many flowers there is as the grass. So we take an area and then we divide it into equal squares, and each one of these squares are known as quadrant. Then we randomly are going to look for some squares. So maybe I want to use this square, about, let's say, 5 squares randomly chosen here, and then I'm going to look for the amount of flowers there's in these squares, and then take an estimate for the entire area that I chose. So here are the steps. We usually mark out the grid lines, and after this we make a table to generate the two numbers in order to choose which quadrants we're going to use. Then we count the numbers of individuals in that quadrant, and then we keep repeat as many times as possible, and then we make the total size of the area. And eventually we get the population size by calculating the mean number per quadrant times the total area divided by the area of the quadrant. Now, I know me writing and reading this is just word problem, and I know a lot of students have a hard time understanding what I'm saying when it comes to word problem. So what I'm going to do here is actually show you an example by writing the numbers and equations so you're able to calculate this in the test. So right here, I'm going to create an area. And in this area here, I'm going to calculate how many flowers there is. So, of course, we have to make sure that these squares are all exactly the same sizes. So, of course, I'm not doing exactly here, but one thing is for sure is that in the test, you got to make sure that these squares are exactly the same size. The next thing is I'm just going to put dots around here randomly as if, these dots are actually plants. So with that, and I'm going to do now is I want to figure out here, it is the population size. Now, of course, imagine this is a huge area. It's impossible for you to go and count every single one of them. So what we do is out of this entire population area here, I'm going to choose 5 quadrants. 5 quadrants. So I will go around, let's say I want to use this one, and I'm doing this randomly. I'm just choose anyone around. So I chose 5. The next thing I have to do is actually count how many plants there is in each one of these guys. So for the first one right here, we have 3. The second one, we have 4. The third one, I would say that let's use it 3. The fourth one, we have 2. And the fifth, we have 2. So I have counted how many dots there is in each of these squares. Now what I need to do is find the average of all of these guys. So I'll add 3 plus 4 plus 3 plus 2 plus 2. So that's 7, 10, 14. Now, when we're doing the average, you got to find over the total, which was 5 of them. So what we have here is 17 divided by 5. Now, 17 divided by 5, it's going to be an average of a 3. So I rounded to 3 here. Now, that means I'm assuming that each square that is in here, there will be 3 of them. 3 for each square. Now, is that the complete absolute truth? No, but I am taking as an estimate. So it's basically I can go here and write 3 on every single box and count them. If I do this, it will take way long time for me to count all the 3s on each box. So there's a faster way of this doing the test. You just count how many boxes on the sides. 1, 2, 3, and 4. And then here there's 1, 2, 3, 4, 5. So you can see there is 4 to 5, so 4 times 5, that means in total there's 20 squares. That's a faster way instead of you going box by box in the test. So now that we know that there's 20 squares, we do 20 squares times 3 because I'm assuming there's 3 on each one of them. So that means the population is 60. So I'm saying that there is 60 plants in this entire area. That means all of this area right here, I'm saying that there is 60 plants, and that will be the answer. Now, this is what random sampling is about. You're just finding the estimation of a population size. by taking some squares. Now there's this different ways that you can do the sampling. You can do it by even space, by random, that's the one I just did, or by zone clustered. Even space, that means I'm going to choose squares with a pattern. For example, you can see 1 square, 1, 2, 3, 4, no squares, then square again, then no, there's 4 of them that I'm not counting. So you can see it's always skipping 4. So there's an even space, so you can see it's all well spread. The random chance is that I don't have anything about putting them in even. I'm just picking randomly some squares. And clustered, I usually will pick them in the large chunks in corners of it. Now, zone 1 is the weakest one because you might miss out a lot of information that is in these corners. So even and random are more likely to be a closer estimate of the population compared to the zone clustered. But this is it. This is for the quantum sampling when we want to find the population size. Now, we're going to the second type of data that you need to be able to measure, which is using the chi-square. The chi-square is all about comparing two groups. So it's when you have two data, two types of plants, when you want to find the association between two species, for instance. You want to see if they're related or if they're not related, if one population is affecting the other or not. So here is the definition for the chi-square test. It can be applied to a data generated from a quantum sampling to determine if there is, and then here's the most important words, statistically significant. That word has to be used every time you're talking about chi-square, so make sure you write the word statistically significant in your test as an answer, where you're saying if there is or there isn't. And what is this trying to say? We're trying to figure out if there is association between distribution of two species. We're trying to say if the population of one species is affecting the population of another. Are they related or not? Now, to do such chi-square, there's 5 simple steps that you must do. The first one is define the hypothesis, right? You got to mention the null and the alternative. Then you have to construct a table in which we are looking for the observed. Remember, the observed is the trial, is the one where you're getting all the data. And expected is the one that you believe to have these numbers before you even do the experiment. Once you have the observed and expected, then you're going to use the chi-square formula, which is this right here, which of course the O is the observant and the E are the expected. This sigma here means the sum, and this symbol here means the chi-square. Now be careful, because chi-square does not mean in the end you have to do a square root. It does not have to do with the square root whatsoever. This is just a symbol of chi-square, okay? After you find the chi-square, the next thing is to find the degrees of freedom. And eventually, from degree of freedom, you will identify the p-value, which always must be below 0.05 in order to be considered as statistically important. So, with that, let's look at an example, which we're going to find the association between two species with quantum sampling and chi-square. So now we're going to combine these two types of data measurements into one. Right here, I found the population area in which I have purple flowers and I have little dotted. And we're going to check them out, these data. But before we can start with this, we have to come with a hypothesis. So I have right here the null hypothesis and the alternative. In the null hypothesis, I am saying there is no significant difference between the distribution of two species. That means the distribution is by random. The alternative one, which is the H1 here, that means there is a significant difference between the two species, which that means the species are associated. So that's my hypothesis. Next, after the hypothesis, I will pick up the data. So I will start by saying, let me count how many squares have none. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 that have none. And I want to count the ones that only have purple. 1, 2, 3, 4, 5. And then I will count the ones that do have both. 1, 2, 3, 4. And then with another color, the ones that only have dot. 1, 2, 3, 4, 5, 6. So I have gathered the data, and it's right here. We can see both present is 4, only dot is 6, only purple is 5, and both absent is 10. But then I have to put in this table. In this table, you must know how to draw this table. And this table is very easy to know. Okay, remember that the word says observed here. That means that's the trials, the experiments that are coming out. That's also the observant that you put on the chi-square equation. So you have the dots on one side, you have the purple on side. Now you're going to have present for the purple, the absent for the purple. And for the dots, you're going to have the present and the absence. And then you make a match. For example, in this square right here, the first one, this one is basically saying in this square, how many of them have both present for both sides. See, present with present, so it's 4. Then on the below square right here, this square is saying it is present in the dots, but is absent in the purple. So present dot is just 6, so you got the 6 here. This square, it says it's absent for the dots, but it's present for the purple, so it's 5. And then here it says that it's absent for both, so it's 10, as you can see here. So once you have done that, you have put the presence and the absence. The next thing is find the total. So you do the total of the row here, which is 9, the total row here, which is 16, the total row going down the column 15, going down the column 10, and then the totals of the totals, it's 25, and this is 25. This number must equal on this side as well as this side. The sum of the both sides should be the same. It should give you a 25. So once you have done this, you have created the table for just the observant. Only the observant, not the expected. Having the observant done, the next thing is to calculate the expected. The expected frequency, it's the row total times the column total divided by the grand total. So this is where having the expectations, which this is coming for the E of the equation of the chi-square, right? We already find the O. To do that, we're going to say the row total. So the row total is this, and the column total is 10, and the grand total is 25. So when we do for the first square, you can see that it's 3.6. Then you do for this one. For this one, the row is right here, and the column is here, so you can see 9 times 15, and the grand total. Same thing here. We have the row is here, divided by times 10, divided by 25. And then here is 16 times 15 divided by 25. So we found the expectations for all of them. That means for when both are present, the expectation is 3.6. When dots only present, the expectation is, let's see, where's the dots present? It's 6.4. When there's only purple present, is 5.4. And when they're both absent is 9.6. So I have calculated the expectation from where? From the observed ones. Now that I've done that, then I have to apply them into the equation. Remind you again that the O here is basically these guys right here. These are the O's. And then we have the E here, the expectation ones. These are the E's, right? The red ones right here, these are the E's. So we're going to apply them here. So we can do for the first one, we have basically here the O minus 3.6 divided by 3.6, and of course the square. So what's that? That's basically the O right here, and then all these based on the presence of both plants, right? And you'll plug it in. So you would repeat this for all of the other sections. So this one is when they are both present. This probably is when there's only the dot. This is when it's only the purple. And then this is only when they both are absent. So you have done for each one of them. And that in total, you will get this. So its chi-square is equal to 0.514. Many students make the mistake of doing this, and that is so wrong. You do not turn that square into square root. You don't. It stays as square like this. Very important. Now that we have found the answer for the chi-square, now we have to apply it to the table, which is a very standard table that you do not have to memorize, which is this table. In this table, there's the degrees of freedom, and this is the probability, right? The probability here, we always using 0.5. This is what we use in biology. So it's very important that you know these numbers. Now, once you have done this, that means when it comes to 0.5, we're always going to use this column no matter what when it comes to bio, okay, because of the 0.5. Now, the question is which of the row, the degrees of freedom. This is where you find the equation right here, which is m minus 1 times m minus 1 again. The m here is the rows and the n is the columns. Now, when you're working with two species, it's always going to come out as 1. So we are working on the first row. So that means we are working on this row right here. That means 3.84 is the number that we're looking for. Let me clear this to make it more easily seen. So we're saying that we are working on a 3.84 right here. This is where we got to figure out about the p-value. So the value is considered significant if there is less than 5% probability. The results are attributed to chance. So when you say less than 5%, we're talking about this side of the area. So on this side of the area, it is attributed to chance. Now, the value is not significant if there is more than 5% probability the results are attributed to no association. That means on this side, anything the number comes on this side, it means no association at all. So in this case, the number we have is 0.514. So we have to look at this row here where it falls, and 0.514 falls somewhere here, which that means there was no association whatsoever. So with that, we do reject the alternative because the alternative says that the species are associated and they're not. So that means there is no significant difference between distribution of two species. That means distribution was random. And this is how we do the chi-square. Remember to know the equation. Remember to work with the degrees of freedom. Know about the p-value because they always ask about the p-value and it should always be less than 0.05. With that, and this concludes the two data measurements. Thank you.